Hello everyone. I am Kuei-Nuan Lin. I am an associate professor at the Penn State Graduate Allegheny. Today, I would like to tell you about one of my research project. It's called a blow-up chemical reaction network, and I would like to thank Professor Somanani for these invitations. And this is a great celebration for me because this is my very first paper research work that is involving chemistry, which is I like it very much. And this paper is not just my work; it's joint work with David Coss. He is a retired professor from Amherst College. Gabriel Sosa, he is current assistant professor at Colgate University. Okay, let me tell you a little bit about myself. I actually grew up in Taiwan, a tropical island that is south of South Korea, Japan, and east of China. It's a tropical island. It's a self-ruled actually, and this is the house of my sister. They actually are currently living here. So even it's a tropical island, many places is still farmers, and we still have rice farms. So my sister family, they are still farmers. And then when I grow up, my favorite fruit is actually lychee tree. Lychee is a very sweet fruit, and my grandpa, they are all farmers. And when I was young, my father decided he wants more than just rice farmer. So it was a little bit rough growing up in the environment I grew in, because my grandpa also lived in the same house. He speaks Japanese because the Japanese colonized Taiwan for a while, and my father speaks Japanese as well because he was educated by Japan. And then the local dialect for the Taiwan people is Taiwanese, and the new government come into Taiwan is actually speak Mandarin. So before first grade, my life was a little bit chaotic. It turned a new page actually a little bit, because being rice farmer, you don't make a lot of money. I have two older sisters and two younger brothers to raise 5 kids. My father decided he wanted to do some business, which is me. He packed the lychee tree from our funds and also collect it from other farmers and pack them and ship it to market to sell for better profit. So starting when I was young, I actually was started 5th grade. I was my father's accountant, because at that time we have to do everything very carefully, adding how much weight for each package, and we send it to the market, and then how much it was sold, and also we have to hire local farmer's wife to help the packaging. And then my father's business get better actually after my grandfather passed away. He completely gave up the rice fund, gave all the fund to his cousin, my uncle. And then so he import machines, semi-automatic packing from United States. And then I started working with my father to fix the machinery, because when you import the machines overseas, there's no customer service. Something broke, you have to fix it by yourself. And that was my 7th grade. I started learning English, and my father was only elementary school degree, so he learned English as well. We two learn English at the same time, to read the instruction manual together and to see if we can fix the machine together. So a lot of time I was with my father, just stand behind him or next to him to help him handling the tool. So that actually make an impact on my interest in the mathematics and mechanical system. And I also really like to draw and also really like to build things. And so actually I did very, very well. After fourth grade, I figured out what people are talking about around me, and my academia grade goes up, and I was able to test into the number one high school. That kind of high school is preparation for going to college. My two older sisters, they actually all went to trade school because no one in the whole family went to college. Actually, I was the only person decide I want to go to college to major in mechanical engineer at the time. So I went to college. I went to all-girl high school, but the school is very far away because we live in rural area. I actually started boarding since high school so that I can spend more time on my study. I end up with the best STEM school in Taiwan, and I'm going to tell you my story after that, after you listen to my mathematics talk. Okay, so hang tight. I want to tell you after I enter the STEM school university, the best STEM university in Taiwan. Okay, so let's go back to the chemical reaction network. So what is the chemical reaction network? Most of you probably knew this already. Nitrogen and hydrogen, they put it together, you put on heat and pressure, you produce ammonia. And here is the chemical reaction. It is a network, right? So this is the reaction component, the ratio, the quantity you're supposed to put in. And here, K12 is the constant. K21, K12 are constant corresponding to how many potential collision actually occur during this reaction, how fast it is. A system of ordinary differential equation. If you haven't take differential equations, actually, as long as you have a calculus ones, the differential equations is similar like calculus one. You have the y plus is equal to ay. This is actually a differential equation. What do we write as dy ds is a constant times y, right? So this is differential. This is actually a differential equation, the equation that involves the variable and function itself. And for this chemical reaction network, what we have is we are considering the rate of change of each component reactant we're giving. So rate of the change of nitrogens is with respect to time t. It's actually negative K12 of how much quantity you put in for the nitrogens and hydrogen to the cube. Where does this cube come from? It's coming from the 3 here, okay? And why negative? Because every time you go through these directions, you are losing the nitrogen. But if you're going the other direction, you're adding nitrogen. So, but this going backward direction, you are depending on the ammonia. So, and you have 2 ammonia, so you do the square here, and K21 is the rate. Okay, so you can do this again for hydrogens, and so every time you go through from left to the right, you lose 3 of hydrogen, and depending on how much reactant you put it in, and then going the backward K21, you are adding 3 hydrogen, and then again you have an ammonia square because here you have square. Okay, so this is actually the a system of ordinary differential equation with respect to chemical reactions you are giving from these productions. And we are mathematicians. Mathematician is actually a translator. We translate the natural phenomena into equations. And equation often we involving the variables, right? So I already assign the time as a t as our variable. So writing nitrogen or hydrogen is actually not what we do. We assign the nitrogen as S1 variable, hydrogen will be our S2, and then ammonia will be S3. And then for the right hand side, the the component of nitrogen and hydrogen, N2 plus 3 H2, we would write it as S1 times S2 to the cube, and then 2 ammonia we will write S3 to the square. And those two sides of your reactions, they are called complex. For S1, S2, S3, they are called species. And if you look at the exponent of your variable for each complex, we can assign y1 is 1, 3, 0 is your exponent beta of your complex. y2 for the second complex, you actually would have 0, 0, 2 because the exponent of S1 is 0, exponent of S2 is 0, exponent of S3 is squares for the 2, okay? And so because of these translations, we just like remove those chemical from our equations. We produce purely differential equation only involving function and its dependent element. So S1, S2, S3, they actually are functions, and then there are quantity you put in for this chemical reaction. Now, if you took you took linear algebra before, this is a system of equations, and we know a system of equation can be rewritten as matrix equations. So we are going to translate further, condense, translate again. Here is what we do. What we write? We do capital S to present the variable S1, S2, S3 vector, and here we have a matrix will be presenting the K12, K21 reactants. These will be coming from each complex, okay? And furthermore, we can decompose the K matrix into product of exponent matrix and the K12, K21 matrix, and this is the complex matrix. So this is how we do it. As a mathematician, we see a pattern, we translate into variable, and then we condense it to make it even more easy to see it from the bigger picture, okay? And so this is kind of a little bit fast, right? So let's do one easier example that you don't get scared away, because if you are not very comfortable with chemistry, right? I have to be honest, I never, really keep taking my chemistry after high school, because I really at the end of the day, I just did my mathematics and then didn't do much of a chemistry. So this is T-cell signal transductions chemical reaction network. You look like this, okay? You have reactions, and you have totally 3 complexes. This is called first complex. This is called second, third, and this will be 1, 2. This is 2, 1, and this is 2, 3, 3, 1. So you have your constant, your reaction rate. And let's do translation. A is my S1, B is S2, C S3, D is S4. And then my first complex, A plus B, will be S1, S2. Okay, my second complex only has C, so S3, and D is S4. And my very first vector will be 1, 1, 0, 0. Be from the first complex. Second complex 0, 0, 1, 0. And third complex will be 0, 0, 0, 1. Okay, so this is my 3 vector. And my rate of change ds1 dt is the same as ds2 dt because they are coming from the same complex, and the coefficient in front of here, they all are 1. And then it will be negative of k1, 2, and s1, s2, because when you go this direction, you lose your s1 or s2. And here is k to 1, but from 2 to 1 is depend on C will be S3, okay? And you also add K3 ones of S4 because this is your direction. You go in and you are adding the component. And at ds3 dt, you can do it similar. So S3 is in here, right? So what do we do? You actually add k1 to s1 s2. This time negative k1 to k21 s3 and negative k23 s3, right? So this is all three you have. I want to combine because we want to write it as the matrix. I say it before as vector product with the k matrix. We will go and call the AK matrix, and those SI the complex vector. Okay, in DS form, you're going to have, and every time you do is here, right? It's positive. I'm going to move it in some place. It's positive K23 of S3, but negative K31 of S4. And so what is your matrix? Your matrix is going to start with D, S, D, T, right? And you have repeat the one because one S1, S2 are the same. Repeat the K1, 2, K2, 1, K3, 1. And here is negative K2, 1 minus K2, 3. And I have 0 here, and I have K, 1, 2. That's so I have repeat. I say it, but I didn't write it. Okay. Plus K2, 1, K3, 1, and then plus K2, 1, plus K3, 1. Now first one is S3. Negative K2, 1, negative K2, 3 for the second column. 0, and then K2, 3, and negative K3, 1 is 0. And we multiply S1, S2, S3, S4. Okay, so this is the first matrix. And now what I want to write it as product of is exponent method, right? So let's do it. So this is the matrix. Now you can write it as 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and multiply with negative K1, 2, K2, 1, K3, 1. They are positive, so I don't do the positive sign. K2, 1, negative K2, 1, negative K2, 3, and 0, 0, and K2, 3, K3, 1, negative. S1, S2, S3, S4. So this is the matrix decompositions for these T-cell transductions. And this is, we use VS because we are, it's a transformation, send S1, S2, send S1, S2 into this vector. So we use VS. Okay, so let's give you official mathematician definition for chemical reaction network. This is the official definition. Chemical reaction network, what do you have? You have N species, those Si, M complex, for example, S1, S2 from previous example. you would have the weighted direct graph. So you have vertex, you have age have duration, and weight, because of those case, the weight of each age. Okay, the vertex, those complex. Okay, the weight of the direct age is reaction rate. This is the chemical reaction network. And what mathematician or what chemistry are interested? We are interested in finding steady state or equilibrium solutions, and which is mean we want this equation equal to zero. We are finding what kind of concentration vector is such that you plugging in this equation equal to zero, and the solution side of this chemical reaction is called complex balance idea. So it's very logical. I always tell my student, I really like mathematics. Any definition we give out is actually very logical and makes sense in terms of what does it mean. Okay, and let's look at one example. What does it mean? Complex balance idea, right? So suppose you have another chemical reaction. I'm going to do a shorter way for my easier pronunciation. 2N2 plus O2 do the two reactions, 2NO2, and the K is the reaction rate. And then you have this differential equation, system of differential equations. You can see in order to have this equal to zero, you would end up with the given reactant NO2 square O2 for each NO must be 0, O2 must be 0. You do not have any reactant at all. And in this kind of situation, we run out of reactants. This situation we call extinction, which is something we are not really interested in. And a lot of time, the really chemical reaction, you could go back. You can reserve the reaction, right? So I'm going to give you another definition. So you have with the red graph, we call it weakly reservable. If for this one is not, what does it weakly reservable is when A can go to B, B can go to C, then C must go to the A. So without the extra age, I draw it. This one is not weakly reservable. Let's do something. The one I just went over, this one is actually weakly reservable. If you play it, you will know any one you start with any vector, any vectors, and then you go to one particular, for example, vertex C, go to the A plus B, the first complex, right? You can go here, and then the A plus C can go with C. And how about D? You can go to the A plus B, but you also can go to here and then go to here, right? So this is weakly reservable. And this is something not me and my co-author invented. It's actually started in 2007. Grayson, Dickinson, Hsu, and Stromfield. And they define they prove it. If you have kinetic component of weakly reservable chemical reaction network, and then you define this particular idea, and they call it toric, they prove this is toric idea. And then you use this, you intersect with the polynomial where you start with those variables, is the complex balance idea of the network, right? So this is the part I'm going to just not detail describe what it is, because may not be very appealing for some of you. And the bottom line is, when I saw this, and then I play with the example, and what I see is I can literally escape this definition, go straight, tell you what is this complex balance idea. Okay, so I'm going to tell you the story behind it. Okay, now this is another example, and you have three matrix 3 complex, and then what they prove, how do they really prove it, why the one I just mentioned, the notation is at the end is the complex balance idea. How do they prove it? They use matrix tree theorems. What does this mean? The AK, remember the AK I talk about, right? So the ds dt is y ak vs, right? They show using matrix tree theorem, they show the AK is spanned by G1, G2, G3. And what is G1, G2, G3? They are coming from the spanning tree with a union sync AI. So let's look at complex ones. This is complex one. You are looking for a tree, which is mean you do not allow cycle. So this is a cycle, okay? You do not allow cycle. And not just any tree, have to use all 3 vertices. And you have to all go the direction, end up with the vertex 1. So this is a tree. And this direction you do K31. This will be K21. This is another tree. Use all the vertices and numbers 1. So this is K23. This is K31. This is another tree. It's K32, K21. Okay. What do you do? Once you have all the possible tree, the first tree, you multiply the each way of your age. So this is K21 times K31. For the second ones, K31, K23. First one, 2, 1, and 3, 2. And so you sum them up. This is your Z1. Then you can do this again for the second vertex. And you find all the tree going down to the 2 and use all the vertex on this graph. So this is K12, this is K32. So that is K12, K32 come from. So what does the matrix tree theorem is? You can find the kernel of an AK. AK is a matrix. Is a matrix. You can define the kernel of a matrix. It's just coming from G1, G2, G3. You span it. It's a linear combination of those 3. This vector spanned by this vector. And so complex balance idea. What is a complex balance idea? We want to find ds dt equal to y a k vs equal to 0. And we know the kernel of ak. So what we need is I need the s1 square, y s1, s2, and s2 square is constant multiple of my g1, g2, g3. What is s1, s1 square, s1, s2 is here. If this is AA, will be s1 square. Here it will be s1, s2. Here will be your s2 square. So your complex vector will be exactly like this, right? And so in order to find complex balance idea, this is the quantity you have to satisfy will be multiple of your kernel of your AK. And what happened is you use calculus 3. When you learn calculus 3, you learn Lagrange multiplier. You literally find a way to eliminate this constant lambda. And then you will end up with a relationship equations will be, this is what you get. And then so these ones, G1, G3 equal to G minus G2 square. It's how people see, that's why they call it, this is a toric idea. Because toric is just difference of monomials, okay? So your complex balance idea is the TG and intersect. Usually people use complex number, G1, G2, G3, and then it's just G1, G3 minus G2 square, okay? And this is where I discovered that I can totally, by skipped the definition. The monoid was infinity. That was very scary. I'm not sure about you. When someone tell me you just do infinite, and sometimes I get scared because what do you mean infinite? How big I should have, right? And that was my undergraduate. And then every time when I started in kickers, I was not very sure what does infinite mean. And then that's why I like my algebra beta, because this is the equation I really talk to me. It's just equal is equal. So I'm going to tell you what do I do, and since I started my study with the PhD. Okay, so this is the blow-up algebra is actually what I really do for the past 15 years of my time. Not just I also do other research, but this is one of main things topic I really like, and I've been working on it. And so we talk about the VF. VF is, you can think about in high school, your teacher asks you to draw plug point on the xy planes, satisfy y equal to s squared. And here you can think about sy is also point, and you want to satisfy this equation. So there's not much difference. So the red curve I have here is exactly all the points satisfy this equation. Okay, and then the curve after blowing up, what does it mean blowing up is when you learn calculus 1, you are taking the tangent line, you are taking derivative of a function. And so literally any point on this curve, you can take derivative. But there's a problem on this point in the center. This point is 0, 0. You cannot take derivative because you would have to tangent line. Okay, and so what do we do in terms of mathematician? We imagine, we add one more dimension. We blow it up. So what does it mean blow it up? We add one more dimension. The curve will right now live in 3-dimensional space. Right hand side, the intersection of the two planes is the blow up of the curve. Okay, so I'm going to let you see one of imitation. This is from Adrian Goins. He right now is a professor in Ponoma College, and also he was the president of National Association of Mathematics. It's great, it's amazing. So he made this programming and put it online. I've been using it because it's so much fun. And here is the curve I start with. In the center, 0, 0, we add one more dimensions. We blow it up, and right now it's 3-dimensional. And then the curve, you literally I'm going to redo it again. The curve, literally, if you look at it in 3-dimensional space, as you see, you blow up the 0, 0 point, it becomes 3-dimensional. Everything is smooth now. So you can just take derivative whatever you want. We call the point that you can take derivative is a smooth point. Okay, and so finding the curve in terms of intersections of two planes is something you learn in calculus 3, right? So the checker ones is these planes. The green one is original. The curve equation, but right now it's in 3-dimensional space. The z variable is free, therefore it look like this form. Okay, so what do? I'm finding the equations such that their intersections describe the curve. after you blow up. Okay, and I'm going to give you official definition. Fixing a field K, if you don't like it, think about real number or complex number. You consider the ring and R is K as modulo out the J. You don't like it, think about J is the ones I was talking about, the S squared plus S cubed plus S squared minus Y squared. This is the J. You can think about like this way using the example. In the Risk algebra of an ideal I, what is this? You can think about this is just S comma Y, because the only the 0 origins is actually me S equal to 0 and Y equal to 0, right? Because remember the J is the curve right curve I did it is me set this equal to 0, and then so my I is my center origin is 0 0, which is my I is S comma Y. The Risk algebra is just the right sum of I to I infinite many power. Okay, and again, every time I see infinite power, I get scared. But don't worry, at the end of the day, we're just looking for the kernels, just like your linear algebra class. Okay, and so this particular pure mathematics notation, Risk algebra is just homogeneous coordinate of the blow up of sped up along VI. Those are just the official mathematics notations, but there's nothing new. Is literally we are looking for what I just showed you example. Okay, let G be the variable. We consider R algebra, and how do you do it? Is G1 I send it to the ST, and G2 I send it to YT. Where's the SY come from? This is SY or this one. Okay. And then this map would have kernel, and not only that, it would introduce one of isomorphism such that the kernel phi is actually isomorphic to the Risk algebra we define here. So for me, since I started my PhD, I'm mostly just looking for what is the kernel, and then go back to the example. What's the kernel? Is just S3 plus S squared minus Y squared, and the one that I show it to you is what? The SG minus Y. Okay, and where does this come from? It's coming from the kernel of this one. How do you see it? Because this map, right, I just need to do G2 times S minus G1 times Y. And what does this mean? G2 times would be, G2 will present as YT, right? This is the same as YT times S. And G1 would present as T times Y. And this is 0. So this is how I find the kernel. And how do you translate from here to here? That is why we have the sped up projected space. We literally just made the new G variable as G2 divided by G1. This is what we do. Okay, as a mathematician, I keep saying we are translator, we just translate. So G is G2 minus divided by G1, and then this equation is exactly as G minus Y. Okay, so from my point of view, I just finding kernels, finding equations. So sometimes my student ask me, what do you do on your research? I'm equation finder. I just find equations. Okay, so let's go back to the kind of connections to the chemical. What is the chemical? And here we actually have the similar definition of original the 4 people paper, and here we extend it. We have union of the graph. We have union of the graph, and we have more variables. What do? We have very similar definition, but each graph we define similar set, and we do similar notation. I keep avoiding this again. This is something you probably have to learn a little bit deeper in the PhD in order to understand it. But it doesn't matter. The end of the day, what I really enjoy my research is I was able to remove the difficult definition, make it more fun, the way I see it. Okay, so we have the same definition, and we actually show this TG is the defining idea of risk algebra. What does this mean? Is TG is the kernel phi I just tell you about. Okay, so how do you find the defining idea? How do you find the risk algebra? Literally looking for the kernel, and let's make this connected to the chemical. So suppose you have a G, the direct graph is weighted, is coming from the chemical reaction network that is weakly resolvable. Suppose your chemical reaction network have a couple components. Okay, so you have G1 through GP, and then this is the definition we defined it before. Then what we have, we do the same intersections. This is the same as the complex balance idea of the network. So our biggest contributions is really we not just do one component, we do any number of components. Not only that, we connect the risk algebra is the same as whatever we find in this definition. So this is the defining equation risk algebra, and if we intersect with the KG, we get the complex balance idea, right? So this is kind of a little bit waving hand for telling you the algebra part. Research show. Let's go back to chemistry. Let's go back to the kernel that everyone can handle and follow. Okay, so remember the matrix tree example. This is matrix tree. Okay, and this is one component. This is 0. Now the extension we have. This is S1 square, S1, S2, and S2 square. Okay. And I tell you the TG is actually the defining ideas of the risk algebra. So we connected this. And the idea how I define it is literally you take these complex vectors. That's it. And then the complex balance idea is TG intersect the K and the new variable, and here I have G1, G2, G3. Okay, so we can just write G1, G2, and G3. Okay, and what happened will be G1, G3 minus G2 squared. And why this is something to do with the kernel? Remember what did I tell you? I send G1 to S1 square T, G2 to S1 S2 T, G3 send it to S2 square T. All right, and then if you look closely from the right hand side, you know S1 square S2 square minus S1 S2 square indeed equal to 0. What does it translate? I put T here, I put T here, I put T here is equal to 0. Again, what does this mean? G1 times G3 minus G2 square is equal to 0. And that is how you see the kernel. You literally find it. Remember, I defined the map. I just find the relationships among the map, and then I find the kernel, and then I have the complex balance idea. Okay, so at the end of the day, I really ignore the definition of what is this one here, because I really don't care anymore. I just care about what is my kernel. What is my kernel? Okay, let's do another one, because this example you still only have one component, right? I want to do two components. Let's do A and then 2A. This is one component. A plus B, C, and there's a B. Okay, so this is actually two component. I'm going to call this is one first complex, second complex, third complex, fourth, and fifth. All right, and so my I1s, I would have S1 and S2 square. My S1, 1, 1. My A is 1, S1. Okay, layout A is S1. Now my I2 will be S1, S2, and S3, and S2. Okay, so I literally just A is S1, B is S2, and C is S3, and that is how I define my variable. Let's do the G variable, right? I have G1, G2, G3, G4, and G5. I have G1, 2, 3, 4, 5. And who is my MG? Will be actually just G1 times G3 minus G2 times G5. Okay, so how do I see it? The kernel. How do I find it? G1 sent to S1 T1, G2 sent to S1 square T1, G3 was sent to S1 S2 T2 because we are in the second component. 4 is S3 T2, and 5 is S2 T2. Okay, and you probably can see S1 times S1 S2 minus S1 square. Let me see, G2 times G5 S1 square S2. This is 0, right? So let's multiply. This S1 is in T, S1, S2 is, this is T1, this is T2. But S1 square, what is S1 square? This is in T1. What's S2? This is in T2. They are indeed 0. And then let's translate. This is the same as G1, right? And this is G3 minus G2 times G5 equal to 0. I'm just finding the kernel. I just totally ignoring this difficult pure mathematical notation. What does infinity mean? I just finding the kernel. If you are interested, I'm going to give you a homework to find the kernel. It's fun to do it. And actually that particular graph, and then the one, the previous example, this one, and the another one, I'm going to draw it to you. Let me use another color for fun. Right, so I'm going to do A plus B. This one is the only one component. B plus C, C plus D, and D plus A. Okay, and then if you try to find a kernel, if this is G1, G2, G3, G4, the kernel will be G1, G3 minus G2, G4. That is how I see it. This is how I, able to see the connection and start working with microprocessors. Okay, so this is my story of my research recently regarding blow-up chemical reaction network. Now I promise you, I go back to my story. After I, finish my high school, I was able to test into State University. It's called National Tsinghua University. The particular school primarily focus on engineer and mathematics. We only have 10 majors, a lot of engineer and mathematics, physics, and chemistry. The school actually was funded to change students to study abroad. So all the textbook other than the history in textbook, everything is actually English imported from United States or Germany or Canada. We have to buy textbook by ordering overseas. And the school actually has a nuclear reactor, so it was very good. Of course, United States came in to shut us down, but it was a fun time. During my time, as I say, I want to become mechanical engineer, and then I went into the school. I actually went to the lab, and I see what people are doing. At the end of the day, I didn't like it. So I need to decide what major I want to do, and I was going to do major in physics because I think physics is a lot of fun. I did talk to my high school teacher because I didn't know if I want to become if I went to the science field. A lot of science field college graduate, they all become teachers, and or they will go to industrial. And then I talked to my teachers. She encouraged me to do mathematics because she told me that if you want to do physics, you're going to do a lot of mathematics anyway, and you're very, very good at mathematics. You should do mathematics so there are more job opportunity for you out there. If you really want to do physics, you always can take extra courses on top of your mathematics. Then now I major in mathematics, and I didn't have time to do extra physics class because the classes are very, very hard. So hard that I think I was very bad at it. Seriously, when I was an undergraduate. And then many of my peers, because the difficulty of the course, they all change it to other field, but successfully, very easily, they change it to industrial engineer, they change it to economy. After they graduate, they have mathematics degree, but they also, a lot of them do computer science. Actually, very few of us become teachers. And my mother's is very, very traditional. And since she knew that I'm very good at study, all she wanted me is to become an elementary school teacher, such that I can go home when my kids are dismissed from school. But I knew I'm not really interested, want to become an elementary school teacher, nor a middle school teacher. I knew I just can't. I don't have patience. And then the professor tell me, you actually are very good at this, which I didn't believe then because I didn't get very good grade. A lot of the math class I had in during my undergraduate, they are B grades, C grades. So I didn't believe my professor, but I really didn't know what I want. I knew I didn't want to go to, just write code. And so I just decided to give mathematics a second chance because when professor say I'm good. And I actually went to the NTNU, is National Taiwan Normal University, the best university in Taiwan to train secondary teacher. And if you're able to graduate from there, the chances are you can immediately get into to teach the best high school in Taiwan. So I prepare the entry exam and study. I get in, it's super high grade, which is what I always do. I try my best. I study. And then now, because my rank when I got in was so high, I finally believe my professor saying that I was very, very good at it. So after I studied a year, the professor at the NTNU, actually they keep pushing me. They are the people I appreciate. Not just 1, 2, 3 professor. After 1 semester, they all tell me, you do not belong here. Go to United States, study, get your PhD. I didn't want to because I'm very afraid of my oral skill in English. And after a whole year of Professor nagging, I finally find some money from my one-by-one tutoring, register the English tutor school, trying to study English. Unfortunately, I didn't meet the requirement for the English for enough grade to able to apply into United States university for PhD program. There's minimum requirement. I went to high school to teach a year, and of course my professor are alright because I really don't belong. I got bored so easily. I love my students though. They are excellent. I really like them because I got the job immediately, just as I expect. After I finished my master degree, so I applied again and came to United States. I got into Purdue University because my family actually against the idea of coming to United States. Nobody went to university, as I told you, and not even mentions go study abroad for a PhD. It just doesn't make sense for them. So I choose Purdue because that is the only university guarantee financial support. I don't have any worry on not finish PhD and have to worry about any financial issue. So I finished my PhD at Purdue University, and me and my husband actually also was in Purdue University. I have 2 babies during the time, during my PhD, and I did extremely well. I really enjoy it, and the Purdue University math department give me as much support they could. I had a lot of fellowships when I was there, and I finished my PhD thesis, and whole family moved to University of California, Riverside, because that was my first job as a visiting professor. I was in California for 3 years. Enjoy working with people. I enjoy teaching, and till now I was very good at teaching as well, because I guess my personality is I try very hard on everything. And so unfortunately, job market crashed during the year of 2008, 2009. There were not many jobs available. I decided to keep doing another visiting positions. There was a Smith College. They focus on more teachings. I want to see what's the big difference between research university, big university, and small college. After 1 year, I applied job again, and then I came to Penn State University, go to Allegheny, that is in the Pittsburgh region. The reason I choose this school is the class size is very small, which something I really like, and I still need to do research, which is something I don't want to give up to choose teaching positions. And Pittsburgh is a bigger region. Would be easy for my husband to get a job, because at that time he didn't get a job, and it turned out very well for our family. 2 kids are happy, and so I got promoted to become associate professor. And actually 2 days ago, my chancellor, associate director, we call it my boss, she just tell me to go up to full professor early. They wanted me to become full professor. So this is my story. I enjoy United States. I enjoy my adventure. I do not regret not going back to Taiwan. Even my family keep asking me to go back. The reason I stay is I really like the research I'm doing, and I also really like the idea of, like today, right now, I actually work at home. So during the day, I'm not teaching. I actually just work at home. I don't have a lot of money, and I don't have big office on my own, but I just stay a corner of my bedroom and do the work, which I'm fine with it, and I'm pretty happy with the time I spend working at home. And when my children need me, I'm available for them. And so my suggestion for those of you want to do mathematics, and then when you finish mathematics, something you could think about. What kind of lifestyle you really like? What is the most important things for you? For me, my family, I really like my father, mothers, but I really like to do my research and working with the people across different nation actually. And here I literally cooperate with my co-author online, and I visit people and I give talks. I enjoy it, and I also enjoy be able to accessible by my children if they really like it. And so mathematics is a lot of fun. Even when you cannot solve questions, you feel like it's difficult, but when you finally solve it after 1-2 years, that is the joy. Nobody can give it to you. The joy, the confidence when you discover and you are the one solve a hard questions, nobody know the answer, is the time you will be very, very proud for yourself. That's it. Thank you for listening, and then I hope in the future, if you're not, you can enjoy mathematics as much as I am.